Hi, this is part 4 of chapter 3 lecture. In this part, we are going to discuss, obviously, as the title says, Bohr's theory of hydrogen atom. This is another crucial part of this chapter in our understanding of quantum theory and electronic structure of atom. Because what you learned in the previous part, part 3, is what is energy is. Energy is basically small pockets of energy releases in the form of particles, and it travels in the form of wave. And what you learn there is, how Maxwell contributed to identifying the energy of a smallest possible pockets of energy in the form of equation E is equal to h nu, and how Albert Einstein jumped in and supports that theory with the photoelectric effects, and he kind of gave a nod to it. So using those equations, you can identify the energy of a photon if you know, let's say, wavelength or frequency. If you know, okay, let me repeat, if you know wavelength or frequency of the light, that your light or radiation, okay? But how do you identify that wavelength? How do you identify that frequency? So this is the part that it is going to address. How do you identify that wavelength of the light? You know how to calculate the energy now using E is equal to h nu equation, but how do you identify wavelength that is released from matter in the form of radiation? So in this chapter, we are going to address that. So in this chapter, specifically, we are going to address how matter absorbs energy in the form of radiation, right? How it absorbs energy from photons, and how it releases energy in the form of photons, and what is the mechanism behind this theory of energy is released in the form of quantum energy, like in the small pockets. Why it is in small pockets, why it is not continuous. That's what we are going to address in this part. And then we are going to reveal how the atom will have this contribution to the quantum of energy by having its ranges of structure outside of the nucleus. So everything you need to know from this chapter, actually, this part is kind of like middle ground for what we discuss and what we are going to discuss, because it is kind of going to reveal both the quantum energy, how it occurs, and what is the electronic structure of atom, right, in this part. So let's get into this topic. So we already know that sunlight is composed of various color components that can be recombined to produce white color, right? Just like if you take the hot iron metal out of a fire pit, and just how it glows with its high energy, because it's absorbing all the energy from the fire, and it is radiating now. So it absorbs and it is emitting. So when it is emitting all of its radiation in different various levels of electromagnetic spectrum. That's why you see it as in the form of just one glow, just like how we see the sunlight as just one white color. And also this red hot color of a metal is also like saying that it is just one huge glow, because it contains all forms of visible spectrum light. So what we are saying here is that the emission spectrum of both sunlight and heated solid are continuous. I would be a little bit more cautious in saying that, we just said in previous parties, energy is not continuous. So that's why let's say, it is almost continuous. We are, using the word continuous cautiously, because it is still releasing in the form of quanta of energy. That's why I'm just not comfortable saying it is continuous. It is continuous in the sense that it comes out all at once, radiation at once, but still releases in the quanta of energy. Because here, as we say, all wavelengths of visible light are present in the white light or red hot glow, and you just need to know how to read it, right? So why I'm saying like all sunlight is almost continuous is because, for example, the light released from the sun, it is almost continuous when it is released from the sun, at that huge, special conditions of reactions occurring at almost close to 6,000 Kelvin temperature. So obviously radiation is huge, and it releases all forms of radiation, like gamma rays through flares, or X-ray radiation, or visible spectrum radiation, radio waves, all of these things. So all of those things are traveling towards the Earth. However, while the sunlight is traveling towards the planet or any other planet, these sunlight are being absorbed by the various different types of gases present in the atmospheric space, and they changes the patterns of the light that comes through these gases. So these astronomers, what do is they study these patterns of the lights, the changes of the patterns of the lights, and they predict what kind of gases are present in the sun's atmosphere by observing the changes of the wavelength patterns of the sunlight. The sunlight should be, having all different forms of visible spectrum, including visible range and, infrared, X-ray, gamma, all of these, but not all of them are being exposed to us because of the gases present in the middle. So just by looking at those missing pieces, based on what gases are absorbed these wavelengths, astronomers were able to predict the different various amounts of gases and types of gases by comparing it with the known data that we have, here with our scientific release data. So now let's discuss what is visible spectrum. We've been saying that there is electromagnetic spectrum, which discusses all different various ranges of light based on its intensity of wavelength and frequency, like gamma rays, X-rays, ultraviolet, visible, infrared, and radio waves, all of these, right? So how do you read it? How do you read into different various lines? So the electron emission spectrum that we call is substance can be seen by energizing sample of matter and see that radiation through a prism. That technique is called line spectra data. We can produce the line spectra of any emission light or radiation at specific wavelengths. If you expose the high voltage source, you can, for example, heat. Well, you can even look at the sunlight also, or you can simply look at the light that in this room through a prism, and you can see that light is actually able to show different wavelengths clearly, because the prism has the capacity to separate this combination of white radiation that comes out of a matter, because high voltage is given to this matter, let's say a hydrogen tube or helium tube or a metal or anything. That matter releases a white light, a combination of all colors. That white light went through a prism after a slit. So prism actually made to divert the different energies and different wavelengths and it is able to separate, because prism has many angles in it. So that separates into specific wavelengths. So these specific wavelengths is what we see on the line spectra. So it's very easy instrument, and it just handheld instrument. You just need to see a prism, very easy. And depending on the type of matter, it has its unique lines. So there is unique identity of visible spectrum region that you can read for each different atom. For example, hydrogen emission spectrum line spectra is different from helium line spectra, is different from argon, and argon spectra is different from neon. Each element has its unique pattern of this line spectra within our visible region. Again, visible region is what we can observe through our eye. So let me just show you a bunch of elements with its unique pattern of line spectra. So when a matter of any one of these, lithium, sodium, potassium, calcium, all of these materials are heated, when they were given sufficient energy, so they start emit the energy back. And when they emptying the energy back, if you put a pressure at them, and if you try to read what kind of wavelengths they were emitting back, and these found to be different types of emitting wavelengths for all of these elements. See, all of these patterns from one to another look different. Those lines are unique. it's like, its identity, their identity. Even for the same group, like alkali metals, like first three, they were all alkali metals. They all have a different unique line spectra. Same group elements will only have, or let's say, same chemical physical properties, but their line spectra is unique for each element, as you can see here. Even for alkaline earth metals, these three here, those line spectra of all alkaline earth metals are not the same. And it is true for all the elements that you're able to read the line spectra for. So far what we know is you have the ability to separate the white light or one radiation into different wavelengths of visible spectrum using line spectra. So now let's get into the details of how we can calculate these wavelengths. I just showed you these numbers, right? These numbers that here are here, 400, 500, 600, 700. But how do you calculate it? What is the science behind it? What are the equations that are helping us? So we are again going back to early 20th century or late 19th century, where different professors contributed different parts of this topic here. Rydberg is one of the professors that first proposed how to calculate the wavelength using the theory that energy that is emitted from a matter is as a result of electron moving from one orbit to another orbit. So he specifically researched on hydrogen atom, and he proposed an equation to calculate the wavelength with this equation of 1 over lambda is equal to Rydberg constant with 1 over n1 square minus 1 over n2 square. And he defined those n1 and n2 as n2 is the larger integer and n1 is the smaller integer. And those n1 and those n's we call in chemistry as, for now they call it orbits, but currently we are calling them as shells. We call them as shells. And you are going to learn about shells from the second part of this chapter. That is really necessary for you to understand any chemical behavior of atoms. What are shells? So for now, you know that Rydberg proposed an equation to identify the wavelength of hydrogen atom. So hydrogen has, let's say, this is hydrogen emission spectra. It has 4 different wavelengths within the visible spectrum, and you could actually come up to identify those 4 different wavelengths just using Rydberg equation, sorry. So where you say this is a larger integer and this is smaller integer of shell, all right? So this is one equation. One common thing that I notice and students commonly say in this part of the chapter is students get confused on what equation to use. So this equation that you are looking at is only to calculate the wavelength of hydrogen element. Only the wavelengths of hydrogen element. That's the Rydberg equation is used for. We have different equations to identify the wavelengths from different matters that I'm going to show you in a couple slides, but this equation is exclusively used to calculate the wavelengths of hydrogen elements. Maybe it is used on some other elements as well, but that's not what we discuss in this chapter, and I don't have those information because that's never our focus here, right? So this is only for calculating the wavelengths of hydrogen emission spectra only, all right? So based on his research, Niels Bohr, maybe from Dutch, is it probably? He's very popular. Niels Bohr, his name is, and he come up with a model to explain why the emission or the absorption of the energy or the radiation of matter in the form of absorption or emission is occurring in the form of pockets of energy that we call as pockets. He has this crucial contribution by saying that the electrons outside the atom actually stays in specific regions that he labeled them as orbits. So this is the nucleus of hydrogen atom, and he proposed that outside of the nucleus, the electron can be found in any one of the possible 6 shells outside of nucleus. A atom can maximum have a 6 shell. Maybe we can have one more now with what we know with more elements that we are able to synthesize up to 118. So at that time, 6 shells is maximum that we know. So he said that when an atom, he said it by producing the hydrogen atom emission spectrum, and his explanation is that based on Rydberg constant equation, he said N3 is greater shell and N1 is smaller shell, right? Then he said, like, if that is the Rydberg equation, these are the integers of n, where n could be 1 or n could be 2, 3, 4, 5, 6. Larger the number and farther it is from the nucleus. And radiation that comes out of the matter is when the excited electron is staying in high energy state and coming to a low energy state. From N6 here coming to N2. From N5 here, something is coming to N2. So when an electron comes from high energy state N6, where it should have never been there. So, well, because this is first time you're hearing how this happens, I'm going to take time and explain why the electrons are in higher energy state first, so it will be more clear to you. So a matter, like if you think of, the very first example I showed, red hot iron, glowing, right? That it is emitting matter in the very first slide of this lecture. It is able to emit the radiation out because in the first place, we heated that iron to highest temperature the iron can be exposed to without being melted. So then it started emitting that because it is an excess energy for it. So what happens when we heat that iron metal or any matter is they receive the energy. How a matter or specifically atom receives the energy is they doesn't go to the nucleus. Nucleus, remember, is highly packed, highly dense, and nothing can go inside the nucleus. Nothing is happening inside the nucleus when it comes to energy. It is a stable area. It is the electrons that has this huge area that they can absorb this energy and they have the room to play around. Just remember, we said, the size outside of the nucleus available for the electron compared to nucleus is compared to a marble that is put in the center of the New Orleans NFL team Superdome. Entire stadium is the size available to the electron to move around, whereas the marble that put anywhere in the stadium is the size of nucleus. So electron has huge space to play with. So in those huge spaces, you will have the pockets or you will have the areas where you will find the electrons from certain distance to the nucleus. Those areas, we are going to call them currently as, well, they were calling them as orbits, and you're going to see that a couple times, but because we are going to call them as shells in our textbook, and in our current days, we are calling them as shells. I'm going to start call them as shells so that you wouldn't confuse. So those areas of where electrons can be found is called as shells. So there is shell 1, shell 2, shell 3, shell 4, shell 5, shell 6. So you would know by the end of this chapter where the hydrogen electron should naturally be present. But for now, you just know that it should be present, closest to the nucleus possible. So that is in shell 1. So when it is not, given any extra energy, the electron is present in shell 1. However, when the hydrogen is heated, so hydrogen absorbs energy. When I say hydrogen absorbs energy, it is actually the electrons takes that energy because they were kind of like freelancers around the nucleus. They take that energy and move to higher energy states, like higher shells. So they go to shell 2, shell 3, shell 4, shell 5, all of these shells. So those shells, high energy state, they will go, but it is not where it should be because there is no electrostatic attractions now when they were at high energy state, so that electron is unstable. so it wants to come back immediately. Everything happens really quick, because remember the speed of the light, the flow of particle is like, a billion times, almost billion times in just a second, right? It all happens very quick. So when they go to high energy state, they quickly find that they don't have a strong electrostatic attraction with the nucleus, so they decide to come back. So when they decide to come back, they have to give up the energy. So that energy, whatever they gave up, is read here currently whenever it happens between shell 6 and shell 2. When it started dropping from shell 6 to shell 2, we are able to read the energy and wavelength of the photon that is released, because electron shed that extra energy out as 410 nanometers. That our eye is reading it as violet color. And all things are possible, all different combinations, but our eye can only read range between 400 to 700. That's why we are able to see only 4. But outside of these 400 to 700, there are many other possible wavelengths that are still happening, but we just cannot see them. So other combinations that we see is 434. Let's see why it happens. When an electron went to N5, it will go to every possible state and come back to every possible state. So when it went to N5, shell 5, when it comes back to shell 2, it released energy that is equivalent to 434 that happened to fall into visible spectrum. And when electron went to N4 and come back to N2, during that process, it released 486 nanometers. And when an electron went to N3 and comes back to N2 shell, it released about 657 nanometers. So these are the 4 combinations that fell into our visible spectrum vision and that we are able to read. So now you know that atom has areas where electron can stay at different levels, low level and high level. And these levels we are going to call them as shells. And when we say quantum energy, it is releasing in the small energy of pockets. It is actually happening because electrons will take that energy, go to different states and come back. And when it comes back, it releases that energy. So quantum energy is actually happening because electrons jumping around between shells. When it absorbs, it goes from low shell to high shell. So it absorbs some energy. It can only take some, right? And when it releases that back. So depending on, if it is going from 6 to 2 or 5 to 2 or 4 to 2, different levels of energy is released. Different levels of wavelengths are released. That's why energy is not continuous, because there are too many permutations and combinations here. It is not continuous because too many wavelengths and too many energy levels that we are dealing with here. Okay. Now let's get back to the lecture, because now you know what is quantum energy is, why photons are releasing. It is because the electrons are spitting out the extra energy that they don't want. That's why photon doesn't have any mass. Photon just has the energy in it because it is the energy left by electron, the particle, the charged particle. Photon is chargeless and massless. So Niels Bohr, his main contribution is that, explaining how these energy levels are happening for an atom. So he developed this hydrogen atom emission spectra by showing where the emission is happening between watt and watt shells, like we discussed in the previous. And because of that, we are able to say that quantum energy and photons are understood, because it is as a result of electron dropping from high energy state to low energy state, or energy is released in quantum of energy models, like photons are absorbed by an atom because it wants to go from low energy state to high energy state. So you could calculate, or we could calculate, the energy of the electrons at different shells using this equation. So this equation proposed by Bohr will help us understand or help us calculate the energy of an electron at a different shell. So all it says is you need to take this constant, multiply with 1 over n squared, where n is a positive integer. They were basically shells. Shell 1, shell 2, shell 3, shell 4, shell 5, shell 6. So we are going to use this equation and develop to eventually calculate the energy of a photon and a wavelength of a photon. This is one of the equation. Again, one of the confusions for the students in this chapter is which equations to use in which case. This equation, as I clearly highlighted here, is useful to identify the energies of an electron at one particular position. If it is present in shell 2, it will have some amount of energy. If it is present in shell 4, it will have different amount of energy because all the difference takes is just n, wherever it is present. All right. So now we already know how to calculate the energy of an electron. We are going to make some comments, right, that are highly useful to understand whatever I'm going to say through the rest of the chemistry course. So I'm commonly, or any chemist instructor, any chemistry scientist commonly is going to use these words whenever they try to explain chemical behavior. Or this electron is in ground state, or this electron is in excited state. What it means is that electron has low energy. When we say ground state, we are trying to say that that electron has a low energy value. When we say electron has excited state, we are trying to say that that electron has high energy value. How do you calculate it? Using the Bohr's equation of En is equal to negative 2.18 times 10 to the power of 18 joules multiplied with 1 over n squared. So when you put smaller integer like shell 1, you would have a smaller value, right? Because it has shell 1 has smaller value than shell 2, we are going to call the lower energy value as the ground state. And because the electrons next to nucleus are pretty tightly attracted to the nucleus, we are going to call these electrons next to nucleus the ground state electrons as the most stable electrons. I understand it takes some time to digest this when I first said it, but it is very important for you to wrap your head around and get this information across. Let me also show you the next one, and we will rediscuss a couple times just to make sure you get this information. So now we know that you could calculate the energy of an electron that is present in the different shells. So for shell 1, shell 2, shell 3, shell 4, shell 6, and 7, you could calculate. Once you calculate those numbers, once you calculate, and you can compare all those 6, 7 energy state values of electrons that are possibly present from anywhere from 1 to 7. And if you compare one number to another, the shell 1 will have a lowest absolute value. So it's the largest absolute value and the lowest actual value because it is multiplied with the negative in the equation. So we are going to call that lowest energy state as a ground state. And based on the attractions between the electrostatic attractions between nucleus and the lowest shell electrons, we are going to call them as most stable state. That is already having lower energy. So lower energy, we are going to call them as most stable state because things will move in chemistry or in universe if they have only potential energy. If it already has the lowest potential energy, it has no reason to move anywhere else. It has no benefit by doing the work. It cannot do work if it has no energy. So shell 1 doesn't have much energy to start with, so it cannot go any further low. So because shell 1 has a low potential energy, we can call it as potential energy, whatever the energy that we are calculating. Because shell 1 already has the lowest potential energy, it is not going anywhere. It is not changing into anything else because it has no energy to do any work. So we are calling that state as least reactive and most stable state because it is least reactive. We're calling it most stable because it is least reactive electrons that are in shell 1. Now let's go to what happens if you find electrons in high energy state. High energy means high potential energy. If you have high potential energy, If it has energy, we can call it as potential energy. In this case, the potential energy means it has the capacity to do the work or transfer heat. So it will do that work because it can, and as a result, it will come down to high energy state to low energy state easily because it can transfer the heat or energy so easily. So we call those high energy states as excited state, and comparatively they were less stable than the ground state. Okay, and I spent quite a bit of time on this slide because it is very important, and I'm going to refer to this ground state and excited state a lot throughout this term. If you get it, it is very good. If you don't get it, talk to me again. We will talk about it multiple times if you want me to. All right, so this is what we know so far. When you give energy to an atom, it absorbs it in quanta of energies. And when I say atom absorbs, the electrons absorbs it and go to high energy shells, and they emit the energy back by coming down to low energy shells. That we were able to show it with the help of line spectra of visible region for different elements. Like I showed you a slide for different elements, how the line spectrum looks. And it is just an example, like general example to understand how it is happening. And you already see the real example of hydrogen atom, how it is coming from N6 to N2, N5 to N2, N4 to N2, N3 to N2, where it is giving 4 different lines for hydrogen atom. Just like that, you know, ball dropping from the stairs is similar example. It drops in the quanta of energy in the steps. So this is how actually photons are released from a matter that we are calling it as, you know, energy, the stream of particles. Now I hope that it is making sense for you when I say it after the part 3 and this part. The radiation is actually both the particle and a wave. Particle is what you could clearly understand here. Electron is releasing some energy in small pockets by dropping from high energy state to low energy state. It is losing, shedding off the extra energy it has. That extra energy is in small pockets, so it is only because it is only carrying small energy traveling alone. We are calling it one as a particle because it is just a thing, right, with small energy. Now, because we know so much about atom electron state, atom has electron states called shells, N1, N2, N3, N4, N5, and N6. Now we are going to label them and use it to our advantage to find a way to calculate the energy emitted by the electron. That is our goal. What is the energy emitted by the electron, right? So in that process, we are going to label the high energy state as NF and low energy state as NI. Those NI and NF, only difference is that one has to be bigger, one has to be smaller. NF has to be a larger number and NI has to be a smaller number. So a photon is emitted when Ni is greater than Nf. Let me pause and make sure I'm saying right. All right, I just took a moment of break to make sure I'm saying this one right because this is so much an important topic. So clearly it says that a photon is emitted when Ni is greater than Nf. What it means is, now if you have different shells, like, you know, one, let's say this is nucleus. Oh gosh. Let me clear the pen. All right. Oh, let me change the settings. Only pen. Now I'm good. So a photon is emitted when Ni is greater than Nf. Now let me quickly draw a atom with electron shell. 2, 3, 4, 5, 6. Let's say this is shell 1, shell 2, shell 3, shell 4, shell 5, shell 6. So for a photon to emit, you need to have an electron in high energy state and drop to low energy state. So what it means is your Ni should be greater than Nf. Let me make sure again. All right, this is a little bit tricky here. That's why I'm just taking a break just to make sure I'm saying this one right. When we say initial state, we are saying where the electron is present when we are doing this study. You're doing the study of when photon is emitted. So for that, your initial state must be a high energy shell. Could be 6 and then coming to 5. Or it could be 6 coming to 4. Or it could be electron in 6 coming to 3. Or electron in 6 coming to 2 or 1. All of these are valid for a emission of a proton. It could be any, your initial state is can be any big number from 5 to 4 or 5 to 3 or 5 to 2 or 4 to 2. Any of these numbers works. Now, when the photon is absorbed, what it means is your final state is should be larger than your initial state. So what it means is, let me try this one again. Nucleus with shells. So your final state this, for example, this should be initial state. It goes from initial state to final state. So energy absorbed, or it can go from this initial state to this final state, or this final state, or this final state. Then, photon is absorbed. So based on this information, when electron absorbs, it will go from low energy state to low Ni to high NF, or when a photon is emitted, where it has to go from smaller Ni to larger Ni to smaller NF, you can propose an equation to identify the energy of an electron by comparing the differences between energy of one shell to another shell. So it doesn't matter if you're calculating for emission or absorption, you could use this equation and identify the change in energy between two different shells of an electron. Either it can be emission or absorption, it doesn't matter. Now, remember this equation. This is very important. Remember, I'm including this equation again in color coding just to show the importance and difference between them. This is the equation just to calculate the energy of an electron present at one point. It can be in any shell. You could calculate it. And this is the equation that you are using to calculate the difference between energy levels of an electron by using this equation, which is basically the energy of a photon, because that difference is what we call the photon is, the emission of a photon or absorption of a photon. Now, using this change in equation, you could also calculate the wavelength of the equation by rearranging our current equation of change in energy by substituting C over lambda in the place of nu in this equation. Because energy is equal to h nu, you can write delta is equal to h nu, and you can replace this nu with this C over lambda. Then you will have an equation to identify the wavelength of a photon, either absorbed or emitted. Okay, these two are very important equations that you require to use it a lot in this chapter. Whenever I ask you to calculate anything, it could be one of those equations most likely. One is for identifying the change in energy, which is energy of a photon. One is to identify the wavelength of a photon. Okay. Now let's see some results of it. You could, using that, you can identify the wavelengths of a hydrogen spectrum. And what you're seeing here is hydrogen spectrum, the visible range for hydrogen spectrum. So hydrogen spectrum has 4 different unique colors that are between 400 to 700. And here you are seeing the clear examples of why it is happening, from what state to what state caused this. I already discussed this when I showed you the Bohr's model of hydrogen atom, but here I'm just showing again just to get the full picture. Same thing. So when an electron is present already at N6, which is, it is present at excited state, and when it comes back to N2 specifically, electron in N6 comes back to any different level, it will, but we are able to read a signal of wavelength when it particularly comes back from N6 to N2. So when it does, it read a particular wavelength that we are able to see in our visible spectrum range. And when an electron present in N5 and it comes back to N2, then we are again able to see another wavelength that we are still able to read with our naked eye. When the electron is present in shell 4 and comes back to shell 2, we are able to see another color code in that visible spectrum range. And when electron is present in shell 3, comes back to shell 2, that corresponds to a wavelength that we are able to see in our visible spectrum. So again, this is only the 4 lines that we are able to see with our naked eye. But again, we have our limitations of not able to see the rest of the electromagnetic spectrum. Our eye can only read anywhere from 400 nanometers to 700 nanometers of wavelength. So these are the list of all possible emissions of hydrogen spectrum that are both including that fell into the visible spectrum range and also rest of the electromagnetic spectrum range. When an electron from hydrogen atom absorbs the photon energy, the bunch of photons of energy, it will go to high energy shells, could be N2, N3, N4, N5, N6, and it will come back to all different energy levels. And these are the different ranges of those energy levels that were identified in addition to the visible range that we are able to see. And these are named after the professors that identified these. And these are the final states and these are the initial states. When the initial state is 2, 3, 4, etc., when they come back to the final state of NF, which means the emission of energy by an electron from high energy state to low energy state, Lyman cities identified them in ultraviolet region. This is the Lyman cities from these states to N1. And the Balmer cities, which is named after Balmer, identified when the electrons emitted to come back to shell 2, some fell in visible spectrum range and some fell in ultraviolet spectrum range. And Passion also identified some signals where the final state is 3 and electrons coming from 4, 5, 6, and they happen to have wavelengths that fell in infrared spectrum range, infrared electromagnetic spectrum range. And the bracket also identified when shell is, the final state of the shell is 4 and initial states are 5, 6, 7, and they happen to fall in infrared range. So what it tells you is that when the matter absorbs energy, the electrons go to all different states and comes back to all different states. But only we can see is just the visible spectrum. For the hydrogen, these are the only 4 lines that we are able to see. But the hydrogen is also exhibiting all of these ultraviolet and infrared range. We are just not able to see, basically, with the naked eye. But they were happening as well. So photon of energy can be absorbed and photon of energy can be released in any different combinations of the shells. All right. Now let's work on the problem. Right. So this is the last slide. Then I'll let you go almost after 1 hour of class or for 50 minutes. So calculate the wavelength in nanometers of the photon emitted when an electron transitions from N4 to N2 state in the hydrogen atom. Right? What series did we just discuss it under? From N4 to N2. Probably Balmer series, so it could fall under either visible or ultraviolet. Let's see. So to calculate the wavelength, if you know the shell numbers, the equation for you to use is 1 over lambda is equal to 2.18 times 10 to the power of -8, and this 1 over n square minus 1 over ni square. When you use that, you are going to end up having to use the Planck's constant and speed up the light constant, because you have a hc in the equation. You will plug that in and you will identify which is your final state, which is your initial state. So let me tell you, this is have proven to be a huge challenge for the student to identify where to plug in which number. If you make a mistake here, the whole problem will be wrong, right? So how do you identify that is when it says emitted. When emission happens is from high energy state to low energy state. And here is the tricky part. High energy state is where the action is starting. So because high energy state is where the action is starting, electron is moving from, you call that state as initial state now, when the emission happens. And this low energy state is the final state. But it is completely opposite when you're talking about absorption. So if you need to make a clear notes with you, you need to make it now. So when the emission happens, the initial state is the larger shell number, and the final state is the smaller shell number given. Okay, write it down. When emission happens, the initial state is the larger shell number, and final state is the smaller shell number. This is very important. In contrast, when absorption of photon happens, the initial state, because when absorption happens, electron going from low energy shell to high energy shell. So when initial absorption happens, the initial state is the low shell number. The final shell is the larger shell number. When absorption happens, the initial shell number is the smaller shell number. The final shell is the larger shell number. Okay? You are clear about that. If you make the clear notes about it, you would avoid a lot more frustration and avoid a lot more mistakes. Right? So when you plug in those correctly and calculate for it, the lambda happened to be 487 nanometers, which fell under the visible spectrum range that we saw previously. So this is all about the Bohr's model of hydrogen atom, and what we learn in this part is really crucial, because you just learn how the photon actually gains its energy. In the previous parts, you learned that light is a wave, and the wave actually also contains particles, but you do not know previously where these particles are coming from. These particles are coming from either absorption of the electrons, from absorption of the energy by the electrons, or release of the energy by the electrons. More specifically, it is because of the emission of the energy by electrons that is present at high energy state to low energy state. That is when these photons are released in the form of particles. Right? Then in the process, you happen to know that the atom electronic structure of electrons is divided in the form of shells. This is very important for you to remember. The electrons outside the nucleus present in areas called shells. Shell 1, shell 2, shell 3, shell 4, shell 5, shell 6. It gets larger, 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 larger. So bigger number goes for larger shell size. And we are going to use that information in the following topics of this chapter and build upon it. It's getting late now. I will stop recording, and I'll see you again in another part in another day.